What's up, you guys? Welcome back to another episode of Wet Math. I'm Will.
I'm Yofi.
And today we're going to be talking about volumes of revolutions.
Volume of revolutions is a fun, easy method for finding the volume of a 3D sphere on a graph. And basically, this is our first video of the series, and we hope you enjoy.
But before anything, you know how we do it over here at Wet Math. We're first going to get wet.
So Will, please douse me.
With pleasure.
God. It's time for the wet and wet math. Just do it.
All right, you guys. Let's get ready to start.
Wet math.
All right.
Wet math.
Okay.
Will, I think it's your turn to get the wet and wet math.
All right. Wet math, you guys. Wet math. What's up, you guys? First thing we're going to cover is revolving regions around the x-axis. It's probably the most simple. That's why we're doing it first. So let's start out by just drawing a XY plane, and let's make a region. So the region's just made up of lines. So let's make one of the lines look like that, and we'll call this line y equals the square root of x. It's an easy equation. The next line we're going to have, because this is not an enclosed region yet, will be right there. And this we will call y equals, my bad. I'm sorry, you guys. It's x equals 3. The last line that we will have to make this an enclosed region will just be the x-axis. So I'm going to go ahead and call the region R. And I'm going to put a subscript of an O right here to signify that it's our original region and not our reflected one, which I'll draw in a second. So the idea here is that we're taking this R region and we're spinning it just from here to here. We're spinning that like that around this line right here. So just to draw what that might look like, I'm going to draw what the reflected region will resemble once it's rotated. We're going to call this region R subscript little r, which will be R reflected. Now, if you guys haven't already noticed, we're using an integral to solve these. And you use an integral because an integral sums things up. And what you're summing up are basically a bunch of little circles. The circles are stacked like this, like that, and they go across from left to right. Now, all you're doing is you're adding up areas of these circles. We know the area of a circle, that's easy. Area is pi r squared. Okay, so we need to incorporate an integral, and we need to incorporate adding up a bunch of areas. So if we want to get the volume. So I'm going to write the volume as v equals some integral, and it's going to be the integral of pi r squared, but since pi is just a constant value, you can pull that out and put it outside the integral. So now all we have inside here is this r squared value. Now, the next step is finding the hard part is actually figuring out what the radius is of these circles. Fortunately here, it's pretty easy. You're just adding up a bunch of circles and all their radii, are like that. There might be one here, and there might be one here, and these both represent really, really skinny little circles, actually infinitely skinny circles, that are just added up, and eventually they make this region. So if we're calling this one of our radii, then we know what this distance is, luckily. It's just this ry value, which is the square root of x. So what we're gonna write inside here is just that. Well, that's our radius. It's simple. That's our radius. Now we have to square it, because that's part of this formula up here. And we know we're doing it with respect to x. So we write dx at the end. The last step of writing the limits, and that's easy because we know this one goes from 0, because y equals square root of x starts at 0, and it ends at this line right here, which we knew was x equals 3. So it's going from x equals 0 to x equals 3, so you're at 0 and 3. Before you do this, it's important to check that all your values in this integral are with respect to x. So we had a limit from, this represents an x value 0 to x equals 3, so those are both in terms of x. We got an x inside the integral, and we're doing it with respect to x. So everything is set up, and we can go ahead and do this. So the best way to do this is to use a calculator. It's easy, you just hit Math 9. I use a TI-83, but Yofi uses a more modern calculator, and he'll explain that in future videos. All you have to do is hit Math 9, and it'll give you something that looks like this. It'll say fn int, and then it'll give you parentheses. Now all it's looking for is it's looking for a y value. It's saying, or it's looking for what goes inside the integral first, and then it's looking for what you're doing it with respect to, and then it's looking for your two limit values. So they're all separated by commas, and the first one was what's inside the integral. And that's easy. It's just the square root of x squared, and that just happens to be x. So x comma. Next one is what we're doing it with respect to. Well, we're doing it with respect to x, and that's going to be the same even when we do it for y, for when we're doing reflecting across maybe a vertical line. It's on the calculator, it still is an x. That'll be talked about in later videos. And then you just do what the two limits are. It goes lower and then upper. So that's easy. Lower one's 0. It goes from 0, comma, and then your next limit, your upper limit is 3, and then you add another parentheses. So that's what we're putting into the calculator. You hit enter, and you are going to get 4.5. And that's how you solve something rotating around the x-axis. Thanks. Alright guys, this is just to reiterate how to do this on the calculator. So we're going to hit Math 9. First one's what goes inside of the integral. In this case it was the square root of x squared, or just x, comma, right there. You're doing it with respect to. If it's just x, it's going to be x every time. Another comma, lower limit, which was 0 in this case, and your upper limit, which was 3 in this case. Type that in, you finish it with another parentheses, and you hit enter, 4.5. What's up you guys? I'm back, and now we're going to be talking, kind of going off revolving regions around the x-axis, but this time we're going to be revolving regions around horizontal lines that aren't the x-axis. Things get a little bit more complicated, but the strategy is pretty consistent, and once you catch on to it, you won't be getting a lot of problems wrong. So let's draw another coordinate plane, x, y. And before we had a region that looked like this. Let's just draw it again. We had one that was like that, and we called that one y equals the square root of x. And then we had it enclosed in with a vertical line. That one we were calling x equals 3. And of course the x-axis. Now before we were rotating around the x-axis, but this time we want to do a different horizontal line. So let's pick y equals -1. So I'm just going to show that with the dashed line going here. We're going to call that y equals -1. So now when we rotate it, it's going to reflect, and it's going to look like this. Like that. This is our original, and there is our R reflected. The problem is, you have this region right in here, and that's going to get rotated too, but you don't want that. And so, before we were using a method where we didn't have to deal with this little region in the middle that we didn't want, but now we have this region. So you use what's called the washer method, and all that happens there is inside the integral, instead of just doing r squared, you want to do r squared of your bigger region minus the smaller region you don't want inside, and that'll give you the volume of just the region that you want rotated. So how we like to call it, what we like to say is r squared, big R squared for your big region minus r for the littler region inside of it. And now before you start these problems, what you want to do is define each one. So in this case, let's draw it first. One of them goes from here to there. That is the r, that's a little r. And then the other one goes from here all the way up to there. And that's our big R. So let's just write R and big R. Now, R is simple, just going from -1 to 0. So we know R is just 1. So we can say R equals just 1. Now, big R is a little bit more complicated, but if you look at it like this, it's kind of simple. That is just the square root of x. Now, since it's down one step, since we're not rotating around the x-axis anymore, it's around the it's around y equals -1, you need to account for this extra 1 right here. So what do? Well, you just add 1. Now, big R is just the square root of x like we had before, but since it's not it's rotated around a line, it's 1 down, you want to account for that by adding 1. So now we can start throwing stuff in the integral and solve this problem. Volume is going to equal, again, always write the integral sign first. Put pi on the outside. Now, the limits are the exact same as the last one, because we want it, it's the same region. So from 0 to 3, except now this time we need to throw this entire thing into our integral. R is root x plus 1, but we want that entire thing squared. So we're going to say square root of x plus 1, square that. And then we want to subtract 1 squared, so minus little r, which is just 1, squared. And we want this entire thing done with respect to x. And the way we write that, we'll put the entire thing in brackets and write dx. Sorry, it's got a little bit complicated with this our y-axis right here, but you can see it pretty well. So right now we're going to input this into a calculator and see what we get for an answer. Our volume, again on a calculator, it's going to be Fn int. Now, what you might want to do is in y1, for y1 you might want to call that your r value, and y2 you call your big R, you call y1 your big R value, and you call y2 your small r value. So let's say on a calculator we were calling y1 will equal square root of x plus 1, and then in the next one down, y2, we'll call that 1. Now the reason we're doing this is so that when we go to the Fn int feature on our calculator, things are a little bit more simple. We're going to be calling this, now it's just this squared minus that squared, because this is that y1 is big R and y2 represents little r. So really it's just y1 squared minus y2 squared. Easy stuff. And then everything else is the exact same, because everything outside the integral is the exact same. It's always with respect to x on a calculator. Just hit x and 0, 3. When we take this and multiply this out on a calculator, you get 11.428, and it keeps going. Since that number isn't an easy number to work with, we just multiply it by pi immediately. We don't just want to throw a pi right on there. So take that number and you multiply it by pi, and your new answer, your final answer, is going to be 35.903 approximately. There you go. All right, guys, this is just me doing this problem on a calculator to show you what it would be like. Again, you just hit math 9. This time we want to go to y1 like we were talking about, clear everything out. Can't see. And then what we're going to want to hit here is square root of x, close that parentheses, plus 1, that's our y1. y2, it's just 1, that one's easy. Go back and type that in, hit vars, y vars y1 squared minus vars again, scroll over, hit function, y2, square that, hit comma, everything else is the same. X, 0, 3, and that's going to come out to 11.42, big number, multiply it by pi, 35.903. Excuse me, you guys. I understand that here at Wet Math we do not make a lot of mistakes, but alas, I have made a mistake, you guys. Just gonna go ahead and uncrumple this. On this one, we forgot to multiply our 4.5 by pi. Okay, it's a rookie mistake. I don't know why you guys didn't call me out on that. 4.5 is an easy number to work with, so we can put that back into fractional form. 4.5 is the same thing as 9 divided by 2, or 9 halves. So it's 9 halves, and then we gotta remember to throw the pi in. That was our one step we forgot. 9 halves pi. And that's our final answer, not that. Thanks, guys.
Hey guys, welcome back to Wet Math. This is the second half of the show, and this is where it gets a little bit tricky. We'll cover the basic one, which is with respect to x. But this time we're gonna do something a little bit different, a little bit more complicated, but we can do it. So, classic x and y coordinate graph, axis. We're gonna use the function y equals x cubed, or y equals x to the power of 3. So let's draw this graph. The way I like to think about it is a little S, a little snake running through the river. So here's the first half, a little backwards S, and then the second half goes down like this. Pretty basic parent function, but we're gonna be looking at just this region here. It's gonna be bounded by the x-axis, and then by y equals 4, okay? And that's gonna be somewhere up here, so I'll just draw this with a dotted line. Y equals 4. And as we'll cover in his video, this is your base region, what we like to call region O or region 0. That just means what we're gonna start with. And the reason why this video is a little bit more complicated is we can't just look at it y equals x cubed. It doesn't work like that, because we're going to do it over the y-axis. This time we're going to reflect it over the y-axis. And this is your y-axis, your x-axis. This is what the rotated region is going to start look like, alright? Because we're rotating over the y-axis this time, the y-axis. We have to make sure it's in terms of y. So, x equals, if we're solving for x here, we multiply both sides by the power of 1/3. So we're going to have x equals y to the 1/3. Okay, x equals y to 1/3. That's what it's going to look like for this one. Now, it's the same process once we have that established. This is going to be our new function though, so y equals 1/3. X equals y to the 1/3. And this is going to be our radius still. And our region is going to be from 0 to 4. So as we wrote before, v equals integral. Remember, put the pi in front. That's very important. Don't want to make a mistake like Will did. That was embarrassing. So put the pi in front here. It's going to run from 0 to 4. 0 to 4. And then the inside, like we said, this is going to be our radius. So it's going to be the radius squared, which is y to the power of 1/3. And then we're going to square it, because that's our radius. Most important step, dy. This time it's in respect to y. It's not dx. It's the dy, because it's all of this in terms of y. So let's double check to make sure everything's in terms of y. This is our function in terms of y. Our limits from 0 to 4. in terms of y, and then it's dy at the end. We're gonna type this into our calculator. Come over here, please. I'm gonna film me. So I was fortunate enough to have the TI-84 Plus. In this operating system, all we have to do is press math, and then 9, and we're gonna get something that looks like this. And it looks very similar to this, right? It's the same symbols. So we just gotta enter it in. So we have 0 to 4 as our limits. Our function is parentheses y. Now the calculator's not as smart as we are, so the only variable we can use is x, but we know it's in terms of y. Y, or x to the power of 1 divided by 3, and square that whole thing. Make sure you put the variable in here, or else the calculator will mess up. It'll take a while. Alright, perfect. So it's 6.047, but remember, we have a pi in front of everything, so we'll multiply this whole thing by pi, and that's our final answer, 18.999. For the purpose of this video, we're keeping it to the thousandth point, so it's 18.999. If we're going to use units, it'll be units cubed, because we're taking the volume of it. And that's pretty much it. Thanks for watching. Looking forward to seeing you next video. Goodbye. Hey guys, welcome to the last video of the day of wet math. And this time we're going to do the same region I just did, but we're going to reflect in a little bit different way. So it's y equals x to the power of 3, or y equals x cubed still. So actually our base region is still going to be exactly the same. It's going to look like this. It's going to look like this, and then our other line is y equals 4, which is up here, and then it's also going to be bounded by the x-axis still. So our base region, r sub 0, is actually exactly the same, and this is going to help us a lot. The difference in this one is, though, instead of rotating around the y-axis like this, which is the easier way, we're going to rotate around the line x equals -2, and that's the line we're going to rotate it around. So this is x equals -2. Sorry, that's a little bit messy. But basically you see what we're doing here. So instead of rotating it like this, we're going to rotate it around this line. So let me draw it real quick. Here. That's going to be our r sub r, or our region reflected. So this one, what makes this a little bit harder, because we have a little gap in between our two regions. The way we do this, though, is the way I like to do it is I like to imagine a point here in the middle of them, and we think of it as two separate radii. This is our first one, our small radius, lowercase r, and our big radius, from here to here, is our uppercase r. And as you recall in Will's video, where he rotated around a horizontal line, we're going to have two separate radii, but our basic volume formula is still the same. We're going to have v for the limit. Our limits are still going to be the same, 0 to 4. Don't forget to put the pi in front. But we're going to have our large radius squared minus small radius squared. So the hard part is finding what our radii are. But we can look at the picture, that can help us a lot. So our big radius for this one is this whole line here, from here to here. So what is that? The way you find that is you add this this region here, which is 2 because it's from negative 2 to your line. So this is always going to be a length of 2, and then you add it to the function, and that's y equals x to the power of 3. But like we said in the previous one, we have to put it in terms of x. Sorry, in terms of y. So it's y to the power of 1 over 3. So our big radius, r, is 2 from here, plus the y to the power of 1 over 3. That's our big radius. We're halfway there. Our small radius is just always going to be 2. Like, no matter whether we draw the line, it's always going to be 2. So our small radius is just 2. So now we have both of our radii. We can put this into the... sorry about that, guys. We can put that into our big volume equation. So V pi integral from 0 to 4 of our big radius, which is 2 plus y to the power of 1 divided by 3. This whole thing squared minus our small radius squared. And don't forget to write your dy. And that's what your whole equation is going to look like. That's what you enter into your calculator. So let's just double check again to make sure everything's in terms of y. Our limits are from 0 to 4. We get that from 0 here to 4 here. 0 to 4. Both of these are in terms of y, and then it's dy. Perfect. All right, now the easy part is to enter it all into your calculator. So we'll please come over here. We type again, math 9. We get this. Our region from 0 to 4. So let's enter that in there. Then our big radius, we'll make open parentheses. We have 2 plus our variable, the power of 1 divided by 3. Square this whole thing. Then subtract it from 2 squared. Come on, Texas Instruments. Let's go. Alright, perfect. So now we have 25.096, but don't forget that we have to multiply still by pi. And our final answer is 78.842, but then it gets rounded to 3. And for being technical, it's units cubed. That's our final answer. Alright, thank you for staying with us for Wet Math. I'm your host, Yofi Weil, and I hope you enjoyed.